recording. And so we start with the boundary value problems. So remember when we were doing all those ordinary differential equations, in all cases, to be able to solve the equation, you will given some initial conditions, right? And the concept of initial condition means that you are given the values for the different dependent variables. So let's say you have a set of differential equations in y1, y2, y3, y4, and so on. Each one of them is a function of time, right? And you have a differential equation, each one of them, and then you are told that y1, y2, y3, y4, y5, and so on, at 0 or at 1 or at 10 at a certain time, right, is equal to these values, right? This is called an initial condition. So when you have the values of your dependent variables as a function of the independent variable at a certain point, just one point of the the independent variable, in this case time, then this is called an initial value problem, or these are called initial conditions, okay? That's typically how we approach the solution, assuming that we have those initial conditions, okay? In some cases, in fact, in many cases of engineering problems, you don't have that situation. You have actually the values of the dependent variable at different values of the independent variable. For example, if you are studying a heat transfer problem, right? And you are looking at a rod. Okay. So let's say you are studying a heat transfer problem. Okay. And you are looking at a rod of a particular material, you know all the characteristics of that material and so on, and you are typically told that you want to solve for the heat distribution everywhere on the material, the temperature, right, as a function of location. Let's assume that location is only one-dimensional, so you are not really looking in the y direction, maybe a very small rod, and it's only extending over a certain x direction, so you are looking at the temperature at every location x, right? And typically you are given this problem saying that solve this, knowing that this side is attached, for example, to a source of heat where the temperature here is T0 at location x0, and knowing that, for example, the desired or the final temperature or whatever on the other side should be some T1 or T final at some X final location, right? So you are not really given the conditions all at the same value of the independent variable. The independent variable in this case is X, right? You have certain values of the dependent variable at some value of the independent, and you have another desired or restricted or constrained value of your dependent variable as at a location, at a different value or a different location of the independent variable. Now this, typically, this happens maybe start end, maybe surrounding in a more, more three-dimensional or two-dimensional problem and so on. That's why they typically call this the boundary value problem, because you are trying to solve the differential equation such that you satisfy the values that are given at different locations or different values of the independent variable, and that's typically the boundary. So if you are solving the distribution of the temperature in this room, assuming that you have an air condition, right, and that's a three-dimensional problem, then the only thing that you know is that if this room has been isolated from the building and it's sitting outside, then at the boundaries of the concrete, at all the boundaries of the room, the temperature outside right now is 32 or 33 Celsius, right? And assuming that the source of your cold air is coming from those slots, and it's coming from the slot with a particular temperature, tell me how it will look like at different locations of the room, maybe after a certain time duration, or even as a function of space and time as well, right? So typically you are trying to solve this problem with boundary conditions, not really with initial conditions, okay? That's the whole idea of boundary conditions. Now, solving with, I mean, all the solvers that we have discussed so far, for example, the ODE 45, ODE 3, 4, and all those ones, and all the methods that we have looked at, the Euler and so on, they assume that you know initial conditions, not boundary conditions. So what if your problem is casted with boundary conditions? What can you do in that case? So this slide just describes what's the difference between initial conditions and boundary conditions that I've just described to you. Okay. Now, if this is the case, what can you do? Forget about this higher order thing. What can you do? The general approach is you do something. The most common approach is called something called, there are two approaches. The most common one is something called the shooting approach. And the shooting, the meaning of the shooting here is that you just try to guess an initial condition, right? And then you try, solve, and see whether this initial condition satisfies the boundary condition that you have. If not, then you shoot for another initial condition. So it's a trial and error approach. Okay? Of course, doing it with a pure trial and error is going to be super inefficient because you keep trying and shooting everywhere. Imagine that you have a target and you don't have a clue and you keep just shooting until someone tells you, oh, now you hit the target. It's going to take forever, right? Typically, if you know some information about the differential equations themselves, you can use that to make, still you use the shooting approach, but you can do better guessing, as we will see in a couple of examples. Now, this slide is talking about, typically, we are not dealing with first order differential equations. In many cases, and the example of the heat transfer that I was talking about a few minutes ago, we deal with higher order differential equations. So a second order, a third order, a fourth order differential equation. The idea here is, and we discussed that earlier also, briefly, we'll just reminder here. The idea here, if you have higher order differential equations, you can always convert those into a set of ordinary or first order differential equations, right? For example, this equation is of second order, and it talks about the distribution of the temperature, right, within a rod, the problem that I was talking about, given a certain temperature at infinity time, so that's kind of the steady state distribution of the temperature, and you are looking for the temperature at different locations, so your independent variable is x, and h is just a parameter that contains several of the characteristics of the medium or the material of the rod itself, right? And the equation, after you do your heat transfer, many of you studied heat transfer, especially mechanical engineering. I think also civil engineering, you study that, or we don't? No?
Industrial.
Industrial. Civil engineering, you study heat transfer, thermodynamics, no? Okay, anyways, so those who studied thermodynamics, so you studied heat transfer, definitely.
No.
No? Not in industrial?
Thermo one.
You deal with thermo one is enough. Thermo one of you heat transfer does not have heat transfer. I think it does. The called Fourier equation for heat. Anyways, maybe when you see it you remember it. But anyways, you don't need to do this here. So the final description comes into a second order differential equation. How can I solve this with the tools that we have learned so far, which are only solving ordinary differential equation? These are first order. Very simple. Assume that the first derivative of your dependent variable is called another variable z, right? So the first derivative of t with respect to x is called z, and then this second order derivative becomes the derivative of z, right? So now you have two equations. One equation relating t to z, so the first derivative of t is equal to another dependent variable called z, and this is one equation, and it is first order equation, differential equation, and then this second order derivative becomes a first order derivative of, with respect to z, of t with respect to z, right? Because dt with dx is equal to z, the second derivative of this is the derivative of t with respect to z, right? And then you can now get two first order differential equations in two variables, right? The t and the z. So now it becomes a set of first order differential equations instead of solving a second order differential equation, okay? I think this should be, sorry, this is written incorrectly. So this should be dz, right, by dx, right? The second order derivative with respect to x is the first order derivative of z with respect to x. Okay, so this was written incorrectly here, okay? So now you end up with two differential equations. Each one of them is a first order differential equation. They all belong to the same independent variable, x, right? And you can solve them simultaneously, okay? Using the methods that we discussed last time, like the ODE, all those MATLAB methods. Of course, that's software. And in terms of description, using the Euler or the successive or the iterative method, any of those methods that we discussed already a couple of lectures ago, okay? So now this is a slide that describes the shooting method that I described to you. So simply assume, for example, that you have been given the temperature at the start and the temperature at the end, right, on that rod. And you have those two linear differential equations that we saw in the previous slide. And now you need to solve using the ODE 45, for example. Now, in order to put the problem into ODE 45, it will require two initial conditions because you have two dependent variables, the z and the t, right? Now, you have only one condition at one location, and then you have the other at a totally different location for the same variable. What can you do? You can go ahead and guess an initial condition for the second variable, the z, right? And then put that initial condition, solve, and see whether the solution that you got will give you the boundary condition that you were supposed to satisfy. If not, then go again and guess another initial condition until you get the boundary condition. Now, if you know that the equations are linear, okay, again, before knowing that the equations are linear, if you know a little bit about the physics of the problem and the general model of the problem, imagine that you guessed, for example, a certain initial condition on the z, the derivative of the temperature, right? And then you ended up with a higher value than the boundary value. And you know from the setup of the problem that the generally speaking, if you increase the initial condition, it's expected to increase the boundary condition and vice versa. Then your next guess is going to be probably something smaller, right? Trying to reduce the boundary value that you will get, and then you will keep moving like a little bit higher. It becomes closer or goes above, then you go a little bit lower, and then you can reach the final solution by doing this repetitive guessing, okay? The other option is if I know that my system is, slide is not useful for what I'm going to say. So if I know that my system is a linear system, right? For example, those equations that we had here were linear differential equations, right? So in that case, I need two guesses. I can do two guesses, whatever values they give me. And then I can do linear interpolation, assuming that there is a line, right, that passes through those 2 points. And then accordingly, I will see, because that line is going to describe the relation between the initial condition and the boundary condition, right? And then since I know the line, and I know what's the required boundary condition, I can figure out in the third trial directly what should be the initial condition, pass that to the system, and you get the solution, right? Did you get the idea? So if I know that the system of equations is a linear equation, a set of linear equations, then this means that the relation between the initial condition and the boundary condition is a line. I do a couple of guesses, one of those guesses will give me, so I guess an initial condition, I will give you some boundary. I guess another initial condition, it will give me some other boundary. Now in the third one, very easily, I'm gonna say the desired boundary condition is whatever I have in the problem. Put that into the line, it will give me exactly what should be the initial condition. And then on the third trial, I will know exactly how to get the initial condition, right? But this is if the system that I'm dealing with is a linear system. What if the system is not a linear system? What's the approach that you can use? There are several approaches, okay? One of those approaches, before we go into the second way of solving those boundary problems, so we are still dealing with the shooting method. One of the approaches, if you have a nonlinear situation, is to try to guess a few points, and then from those few points you can get some kind of a polynomial, maybe third order, maybe fourth order, and then do the same thing. Once you fit those to a particular polynomial, you can actually go and see what's the desired boundary condition, and from the fit to the polynomial curve, you can get what should be the initial condition to get you there. Most of the time, this polynomial approach will not get you to the exact solution because it's very hard to guess how the nonlinear relation looks like. It might not be a polynomial in the first place, right? So that's still something that can get you to an approximate solution. So for the nonlinear, this slide is useful for the nonlinear, right? So an example here uses an approach for the nonlinear, which is basically trying to solve for something called the residual approach. So if I know by solving, and now I guess, for example, I give an initial guess, right? And then once I give that shooting or initial guess, I can solve the problem, right? Solving the problem is gonna give me a function that relates my dependent variable to the independent variable. So I have the solution right now, right? I know that that solution in terms of the shape is correct. It's only gonna be shifted due to the fact that I gave some initial condition that does not result into the correct boundary condition. So I will take that equation that results from the initial guess, call that equation, for example, f of my initial guess z1, for example, okay, or t1, okay? And then I will subtract from that the desired final condition. Let's say the final condition says that the temperature, or the boundary condition says that the temperature should be 400 Kelvin at the end, right? So I will take this and then subtract from it, I take this evaluated at the final location, right? So it evaluates, for example, to 200. And then I'm gonna subtract from that the difference, this value minus 400 will give me the difference. I'm gonna take that difference, plug it into the equation, or in other words, I'm gonna fit the equation, the one that represents the solution, such that it gets me the final by finding the zeros of that equation, solving that equation, such that it satisfies the boundary condition, and accordingly I can get my initial condition, take that initial condition, put it to the solver, and then you will get the correct solution, okay? I think doing this by example is what we need to do right now. So let me, I'm not gonna use the written code immediately. I'm gonna try to describe to you how this looks like. Just, don't forget it's So let's try to do this step by step, just to get the numbers, not the analytic part, no. Shooting part. Okay. So let's do, I think, okay, let's do first the come on. Let's first do an example on the linear case, and then we go back to this slide. So let's get this guy down. And let's do the example on the linear case. So use the shitting method to solve. So here is your differential equation. So differential equation is, yeah, d2 t by dx squared plus h dash, I will tell you the values of those parameters, multiplied by t infinity minus t, and that is equal to 0. And the conditions are generally that t at 0 is equal to some initial value, we call it TA, and then t at the length of the rod, the end of the rod, is equal to some boundary value TB, and the values for those parameters are as follows. So L is equal to 10 meters, and H dash is equal to 0.05 meter to the minus 2, and T infinity is equal to 200 degrees Kelvin, and T0 is equal to, T of 0, T at 0 is equal to 300 Kelvin, and last but not least, the boundary value at length 10 is equal to 400 degrees Kelvin. Okay. Now, if you want to solve this problem, we said first that you have to define your, convert this differential equation into two linear differential equations. So it becomes, the first one is dt by dx is equal to some newly defined variable, we call it z. And then the second one is going to be dz by dx plus h dash. H dash is 0.0, yeah, so 0.05 multiplied by t 200 minus your t, so that stays as it is, right? And this should be equal to 0. So these are the two differential equations that you need to solve, okay? And so just to follow the same numbers here. So now we have this initial condition, and then our next guess on an initial, we don't have any initial conditions on Z. So let's assume that the initial condition on Z says that a value of -5 for the initial value of Z. So let's assume that we also have some initial value for Z, Z0 equals to -5. Don't forget that Z is dt by dx, right? So basically the units of this is gonna be what? It's temperature with respect to length. So it's gonna be Kelvin per meter, right? It's the rate of change of temperature as you go over the length, right? So assuming that this is the initial value, now you can go and solve this. How would you solve this? Solve this using MATLAB. I'm not asking you to solve this with like do Euler by hand or anything. So if you want to solve this problem by MATLAB, you have two initial conditions, right? So you have initial condition on Z, and you have initial condition on T. This is just a guessing, so we don't know if it's correct or not, but this is given to you already. Where is it? T of 0. That's the initial condition that we have, right? So this is already given to you, right? And the other one is a guess. But anyways, now you need to solve. You have two differential equations, linear, ordinary differential equations, and you have the initial conditions. How can you solve those? Anyone is practicing or doing anything? So how do we solve this in MATLAB? In MATLAB, what do we do? Remember, we do this in two steps, right? First, we define the functions, and then we pass them to a solver along with the initial condition, right? So let's say the solver, just to follow the same here, we will use the 4, 5. So the range quota 4, 5, right? So ODE 4, 5. Okay, that's the function that we call to solve, right? Now how we define the functions, how we define the equations to pass them. يا جماعة. No? Nobody remembers? So can you go to the slides of not last one, but the one before? So the ordinary differential equation. It had a lot of programs that describes how to solve this, right? And you tried to do one in the class as well, right? Remember that example that we did in the class? We tried to do an example last time where you plot both, right? You solve and you plot both functions. If you still have that code, you can look at it. If you don't, you can look at it in the slides. It's almost written here anyways. If you can see that small slide that I made it very small, it's almost written there. Anyone figured out?
So we find them as vectors, first element T and the other one is Z.
Huh? Sorry?
We define them as vectors.
Okay.
So the first element would be T and the other one Z.
The first one is gonna be T, اللي هي temperature. Yes. Yeah. Yeah. So go ahead. Write anything. Okay, so let me remind you a little bit. So ODE, maybe this will remind you a little bit. 45 is supposed to take, now everything goes together. Okay, so let's do it. Let's be smarter. ODE, the solver, is supposed to take three things. Tamam? What are these three things? A pointer to the functions. The functions are typically described, if they are multiple functions, they are described in a vector, right? So it takes a pointer to that vector. Let's call it, for example, y or whatever, okay? Okay, or sometimes just to make sure they call it dy, for example, okay? And the second parameter that goes there is range of solution. So I want to solve this for the range in terms of the independent variable. So I want to know the values of the temperature at every point in the rod, and we know that the rod goes from 0 up to 10 meters, right? So that's the length of the rod. It starts at 0 and it finishes at 10 meters, right? And then the last is gonna be your initial conditions as a vector. So one value for each dependent variable. We have here two dependent variables, right? One of them is the one given, the 300, and the other one is the one that we guessed, the -5, right? This is how you will call the solver. The question is, how do you define this? How do you define this dy such that it holds those two equations that we see up there? Anyone remembers? So I will write the text, the syntax for you. So dy is equal to a vector, and that vector has, let's say, for example, we call the independent variables y. So y1 and y2. So we have y of 2, the second one, right? And then we have, so whatever is on the left is the derivative, right? And whatever is written inside here is the right-hand side. So if you want to write this the correct way, you should take everything to the other side. Okay? It becomes dz over dx equals minus 0.05 multiplied by 200 minus t. Okay? So the first one is easy. The derivative with respect to the independent, which is not written on the right side, it's always on the left side. So that derivative is equal to z. So that's why we say it's equal to the variable as is, right? The variable z, and we call that y2, okay? Y, the second one. And then this, we have the z, which is, again, what to say? Yeah, sorry. This one is the, yes, okay. And the second one is the differential equation, which is dealing with another variable. Let's call that y1, okay, is equal to, so the derivative is equal to minus 0.05 multiplied by 200 minus, okay, your y1, which is t. Okay? Did I write this correctly?
So Y1 is the temperature, the initial temperature.
Sorry?
Y1 is related to the initial temperature, right?
Not initial. This is the dependent variable مباشرة. Y's are the dependent variables. So one of them is the temperature. The other one is the derivative of the temperature. Okay? So the differential equation is written as the whatever here. Okay, and then the derivative of the temperature is called z, right? And that is y2. And in this case, the differential equation here is dealing with the derivative of that z, which is another variable, y1, equal to the z is y2, sorry. the derivative of the second one, y2, is equal to whatever as a function of y1. Okay, so this is y1, t, and this is y2. Right? And the differential equation here is, here we have a derivative with respect to with respect to x, the independent variable. And for the first one, it's so for this, it's the derivative of this. For this, it's the derivative of this, and so on. So it goes that way. Okay. So this is how you write the equations, and then you pass that to the solver, and the solver should give you. Can you try that? Can you try writing this on MATLAB? You should be able to get it maximum in 3 trials, right? So 2 trials will give you 2 points to fit the line 2, and then the third one is going to be directly for that final boundary condition, what should be the initial condition, and then you take that initial condition, put it into the solver as you saw, and you get the solution for your problem. Okay. The other approach that I wanted to also test with you, and that one will include a bit of extra coding. So let me see where. Yeah. So this is the case where you have nonlinear. Okay. Yeah. So for the nonlinear case, the problem is slightly changed. So so for the nonlinear case, let's say that you take into account more issues of the heat transfer and losses and stuff like that. So your differential equation becomes d2t by dx squared plus h dash times t infinity minus t plus some other parameter sigma dash multiplied by the temperature, the steady state temperature raised to the power 4 minus the temperature to the power 4. So now you have this extra component that makes the expression no longer linear, right? Because you have this as a function of the temperature to the 4th power, right? And this is equal to 0. So this becomes your second order differential equation that you need to solve. Again, the same approach. So the first thing is to convert this into 2. They are not going to be linear, but 2 first order differential equations, right? So it becomes dt by dx is called z, and then the second one is going to be dz by dx is equal to minus h dash multiplied by t infinity minus t plus, minus sigma dash multiplied by t infinity to the power 4 minus t to the power 4, right? These are your simultaneous differential equations that you have to solve. Now you need to solve. One way to do this is to keep guessing, right? So again, before going into the more elegant approach, let's just try to put this similar to what you did right now. You have seen an example for the solution. So go and define that function and input those 2 equations into the function, and then put the solver, guess an initial condition, and produce a single solution for now. Please go ahead and try. Okay, I'm gonna give you the values for those parameters. So HL is equal to 10, that's the total length. H dash is equal to 0.05. T infinity is equal to 200 Kelvin. T at 0 is equal to 300. T at the full length is equal to 400 Kelvin. So nothing changed. You just need sigma now, right? Where is Mr. Sigma? Sigma, yeah, radiation, sigma dash bulk heat transfer, yeah, sigma dash is equal to 2.7 times 10 to the minus 9. Yeah. And this one is Kelvin minus 3 meter minus 2, the units. And this one is meter minus 2 H dash, right? Meter minus 2, and this is meter. So these are the different parameters that you need to substitute in those equations. So again, you just need to do that, maybe call it again function dy equal. Do you say equal when we define the function? Function dy equals something? Or what do we say? Equal. And then whatever you like to call that, dx, dy, and مثلا أي حاجة, whatever. Okay. And x comma y. And then inside this function, you need to put the two equations the same way we did before. Mm-hmm. Oh. Anyone got anywhere? Got anything anywhere? You don't want to try? Hmm? What diverge? To 10 to the minus 9. That's what the value they have. It's 2 to the minus 9. Yeah, 1.6. Sorry, 2.7. Yeah, 10 to the minus 9. وانت كاتبها ازاي 10 to the minus 9؟ ما انت you started with one لا not good. استنى هقول لك انا good start point to try لان اعتقد this was gonna take you really far away. It's probably why it cannot solve. So use as an initial guess something like maybe minus for the second initial condition, use something like minus 30 ولا حاجة. Minus 30, minus even 35.
It works. Minus 69.
Minus
69.
Okay.
It needs a measure.
هجرب minus 45 كده. So yeah, use something higher than minus, maybe higher than minus 40. So minus, sorry, lower than minus 40. So minus 45, minus 42, minus 43, minus 50, something like that. Then you can get some initial guess. Anyone managed to get anything? You managed. Online ده صعب. انت طيب managed to get something. How do you define functions or anything? It's very difficult to do it online.
You can. Yeah, it's it.
Okay. Anything? أي حاجة. مش أي حاجة تانية. شايف فيه بقى. ماشي. طيب. Okay. So now.
استخدمنا نفس الابروتش بس السؤال اللي فات
اه.
طلع حاجه يعني
مش مهم هو طلع بس طلع معاكم solution. This is not a correct solution. Yeah, looks good. But as you see, the boundary condition is not satisfied. Which curve is this? The y1? Yeah, that's y1. So you see that by your guess, whatever you guessed the minus 45 مثلا. What's the final condition here? It's almost 120 مش كده? While the boundary condition should be around 400, right? So this means that this initial guess is not correct. Now you can keep on guessing until you get something, but it might take you, because this is not non-linear, or relation even is not clear. You increase, sometimes it's going to take you up, sometimes it's going to take you, so you don't have a guess. The approach here is kind of twisted a little bit. I tried to describe it in words earlier, but might not succeeded completely. So the approach here is as I mentioned, okay? When you do that solution, so imagine this, you did the ODE, right? 4, 5. and then whatever you pass there, and supposedly it returned for you a solution, right? Now that solution, the curve that you got, right, was not correct because it did not hit the boundary condition. So what you do, you define a residual function, which is the difference between whatever you got in that solution and the desired boundary condition, right? So let's call that residual, right? And that residual is basically whatever solution, call that the solution. So that residual is the solution that you got minus the desired boundary condition. So minus 400. And now your objective is to change the curve that you got, right? So this is, think of this as an equation, some equation, that's the curve. And then you shifted it such that it fits at, sorry, it's not the 400 directly. It's the difference between whatever boundary, it's okay. I'm gonna describe it here better. So assume that you have the solution, and then you have that solution at point length x equals 10. So that solution is basically a curve. Now you have that solution at 10, تمام? Which gives you, in your case مثلا, was almost 200 or 150. Yeah, 120, okay? Then minus the 400, that's the residual, that's the difference between both. Take that value, this whole thing, and subtract it from solution as it is. So as if you are trying to shift your curve such that the last point of the curve, you are trying to shift the curve up, such that the last point of the curve is going to be 400, اللي هو desired boundary condition, تمام? And then you say, give me the initial condition from the newly shifted curve that satisfies this, تمام? So the way you do this is that you define a function called the residual, and that residual function is gonna be the solution minus whatever we call this. We can call this difference, for example, okay? So minus diff, okay? So that's the shifted curve. And then you want the initial point that corresponds to that. So you tell this equation, this is now a new equation, right? Now you want to solve this equation such that it gives you a value equal to 0 at the end. Because there's gonna be no difference between what you get from this and the desired boundary, right? So you say, give me the 0 of this equation. Now it's gonna return to you what's the initial condition from that solution, from getting the 0 of that, and then you take that initial condition, you plug it into the solver again to get the actual solution, right? So let's look at the code. I think coding this is not gonna be easy, but let's try to look at the code snippet that does this. Let me see. I'm trying. Okay, how can I do this? Here is what you will get after you do this. So now, as I mentioned, the next step is going to be, this just shows you when you are not doing the, like just guessing, right, with minus 50. So this is just guessing. The minus 50 is something else here. So this is already with what you desire, right? So ordinary differential equation, you pass, yes, this is the solution, okay? And you plot, you figure out the two approaches, okay? Because it already uses the the residual one, okay? Okay. The other approach, before we go to the other approach, do you have any questions so far? Some stuff are easy, some stuff are a little bit confusing, but the best is you try some code yourself, okay?
From the temperature curve, get the initial conditions substituted, he said,
Okay, so that function called 0. What it does is, yeah, so what we saw in the previous slide was something else. That function that called zeros, what it does is, it tries to manipulate the curve. So imagine this curve as a function, okay? And then you have subtracted from it some value to make sure that it will fit. Now you solve this equation such that you guarantee, okay, that it gives me 400 at the boundary. When it does that solution, that 400 at the boundary is going to correspond to a particular initial condition at the beginning, right? So it's trying to manipulate the curve until, again, the curve is going to be a function between the input, the distance, and the temperature that you get at every location, right? So the location and the temperature. It's going to adjust the curve such that it will give you a 400 at 10. And what you will get from there is going to be what should have been the initial condition. So it's as if it's moving the initial point. What should have been the initial condition so that I can get that final or boundary condition. So that value that comes from the 0 function that we used in MATLAB is going to be your initial condition that you will plug directly into the solver again, the ODE 45, and then you will get immediately the correct solution.
Graphically, you get the initial condition from the other curve, not the temperature curve.
Yes, it is from the temperature curve, but
You have the initial condition is 300 degrees.
initial condition. No, that's the initial condition for the second function. Now we are trying to guess the initial condition for the derivative, no z, not t. Yeah, the equation that we are dealing with is what is the one for z, not t. We are trying to figure out the initial condition for the z. Okay. The other option to solve differential equations that the other option to solve differential equations with boundary problems, and this is kind of an introductory part to your finite element, is using difference equations. So you go to the differential equation itself, and whenever you have derivatives, first order derivative, second order derivative, and so on, you represent those as finite difference, right? So you know how to do that, right? So it's just, for example, if you have this equation and you want to convert that into a finite difference equation, if you have a second order derivative is typically represented by difference between three values. So you are getting the derivative at ti. This is dependent on the next one and the previous one, and it's divided by square of the step. The delta x is the step that you move, so you discretize your independent variable, in this case it's x, and then you calculate the derivatives as a finite difference. So this equation becomes written this way. At any point, at any temperature, at any location, xi, right, is represented by this equation as a function of the next one and the previous one. Okay, so now you have the temperature at location I, which is a function of the temperature at location I plus 1 and I minus 1. This is because we have a second order derivative. If it was a first order derivative, it would have been temperature at I and either I minus 1 or I plus 1, depending whether you use forward difference or backward difference. Okay, and then the equation becomes, as you see, right? There is no differentiation or anything. It just becomes a linear equation. Okay, in this case, it's linear. It might become a nonlinear equation if we had a nonlinear differential equation. Okay, so it becomes a linear equation. The only thing is you introduce more variables. So instead of solving only for t at location I, so that the temperature here, at any solution step, you have the previous one and the next one. So the set of equations that you will have for this are going to be represented as a set of linear equations, and it's always at any place, right? You have the current, the previous, and the next, right? So you can imagine that if you write the matrix that represents those set, again, the equations are going to be for what, by the way? They're going to be for t0 So t at location 0, t1, t2, t3, t4, until you reach whatever. So let's say the 10 meter, you are going to divide that into centimeters. This means that you will have 1,000 t's, right? Each one of them is a function with the next one and the previous one. And for the first one, it just the initial condition defines it. For the last one, the boundary condition defines it, right? So you reach T1000, which is supposed to be T at 10 meters. And that one is actually the 400 Kelvin given as a boundary condition. And we are talking about T at location 0, the start of the rod. That's the 300 Kelvin, right? So now you incorporate all your conditions, whether they are initial or boundary conditions, okay? And then you start solving the set of linear equations, right, that you have in order to figure out the temperature at every location, okay? And as you see, it's always, for each one of those, it depends on the previous and the next one. That's why your matrix here is gonna be only triple diagonal, right? So only 3 diagonal lines and the rest of the matrix is 0. Because in every equation, you only use the current, previous, and next. Current, previous, and next. But the other variables do not exist, okay? This makes the solution easy because it's just, they call that a sparse matrix. And not only that, it also have diagonality to it, which makes the solution much faster and much easier to approach, okay? Again, how to solve this is go back to the solvers that we talked about in terms of linear equations. That's just a set of linear equations now, okay? Sometimes you don't have the boundary conditions on the variable itself, T temperature in this case. You have some conditions on the derivative of that. Again, you can still, this slide just shows that you can still incorporate this into your equations. Okay, so simply the equations again includes everything, including the derivatives and so on. So if you have a boundary condition on the derivative, you can still incorporate that into the equation itself. Okay, so that just shows you how to incorporate that. I just want to go quickly to the next part, the eigenvalues. I'm gonna quick for nonlinear. It's the only thing is the slide before this one was talking about what if your equations are nonlinear. Again, a set of nonlinear equations, you can use Newton-Raphson or any one of those methods that you can use to solve nonlinear equations or iterative approach or whatever. Again, you just convert your differential equation into a difference equation, but in that case it becomes a nonlinear difference equation. You have a set of nonlinear equations, you can solve them with one of the iterative methods that you have studied. Maybe in this course we talked only about 2 of them, or in some other course. So that they become regular non-differential equations, okay? Here it talks about some important MATLAB commands that you can use to solve problems that includes the boundary value and some of the tools also that supports this, such as the ODE function, BC function, boundary value P initiative, and so on. Just it's for your reference. You don't need to go through them, and a couple of examples using those functions, okay? By this, I think we are done with the boundary value. So the whole idea here is what we do eventually is that one of 2 approaches. Either we use the typical solvers that we used before, but we need to convert the boundary value problem into an initial value problem. The way we do this is by the shooting approach. But to make the shooting or the guessing more efficient, we have to kind of capitalize or exploit the structure of the problem that we are trying to solve, either by knowing the behavior from physics, so that gives us a guide whether we need to increase or decrease our initial guess, or if we know that it is a linear system, then we can figure it out in 3 trials only, or if it's a nonlinear system, then we can use the zero forcing approach, or the approach where we force the curve to kind of provide the required boundary value, and then we check to figure out what's the corresponding initial value using the zero methodology or the zero function from MATLAB. Okay. The other thing that we need to, the other approach to solve those equations is using the difference approach. So you convert the differential equation into a finite difference equation, and then you solve that. Okay. This is kind of, as I mentioned, introductory to what you do when you are approaching finite element. But the difference is that in finite element, you are typically dealing with partial differential equations. So you have multi-dimensions. Okay? You are not just dealing with ordinary differential equations, or you are not dealing with ordinary differential or single variable. Because here, the independent variable is just always one thing, either x or t. That's just one variable. In the finite element approach, you are dealing with more than one independent variable, and you start having partial differential equations. Okay. Eigenvalues. Remember, what's an eigenvalue? Quickly, كده. When we have a matrix and we calculate the eigenvalue and the eigenvector for that matrix, what are we looking for? What is that eigenvalue or eigenvector? Aside from the equation that allows you to calculate them, what does it mean? Anyone knows?
Have some meaning. It is like a vector that has like certain direction, not a change when you are multiplying.
Yeah.
And it will give only scaling
Yes.
in this direction.
Yeah. So first of all, when you multiply a matrix by a vector, what happens? It's a transformation, right? So and transformation will include two things. It's going to be some kind of rotation and then some kind of scaling, both together, right? That's what a matrix does when it's multiplied by any vector. Okay? So it means that it goes to the space where this vector exists and it transforms that space. Okay? Now, within the space, okay, if we look at the eigenvectors of that transformation matrix, we'll find that those are certain directions within the space that when you impact them with the matrix, they don't change their direction. They stay in the same direction, but they just, so the whole space is being kind of tilted and scaled. But those particular directions within that space, they will only scale up or down. Maybe change like reverse direction, but they are not gonna shift away from their line of direction. Okay? How can this be useful? An example of this is if you have a three-dimensional object and you want to figure out what is the axis of rotation. Right? The axis of rotation is gonna have so if you have a cube and you have multiplied that cube by a tensor, right? Or a matrix, a three-dimensional matrix, right? So you are kind of rotating and maybe also, right? Now, if you are looking for the rotation, what was the axis of the rotation? You can see that the axis of the rotation is the only vector that is not gonna change direction by the transformation that you did, right? So finding the eigenvector or using the eigenvector approach, you can actually find the axis of rotation for a particular transformation. Because that's the direction that's not gonna be rotated when you are doing the whole rotation. Everything else is gonna be rotated except only along that direction. It's only going to be scaled, and in fact, if it is an axis of rotation, it's not even gonna be scaled. So the scaling is gonna be equal to 1. So it will have an eigenvalue equal to 1. What is the eigenvalue? The eigenvalue is the value of scaling along those eigenvectors. How big or how small they become when they are affected by the transformation. خلاص؟ المهم. So this is represented by two equations. The first equation says that when you have a matrix A, if you multiply that matrix by an eigenvector, the result is gonna be the eigenvector scaled. So lambda is a scalar value, it's not a vector. Okay, while U is a vector, A is a matrix, so this is a vector, and A is a matrix. Okay, so the eigenvector for a matrix A is the vector that has this property. If that vector is multiplied by the matrix A, the result is going to be the same vector scaled in magnitude by some constant value. Either becomes bigger or smaller, or it can be scaled by a negative, which means that it will reverse direction, in addition to becoming bigger or smaller. Okay, so now U is an eigenvector of A. Okay, now the other property, which is the eigenvalue, okay, says that if you are trying to solve this problem, A minus lambda I multiplied by some vector x is equal to 0. If you are trying to solve this problem without really, because the trivial solution is that x is equal to 0, right? But you are trying to look for all the other solutions where x is not equal to 0, okay? So the non-trivial solution, then the solution to this problem, or you can actually satisfy this without requiring x to be equal to 0, only if, or you can find a solution for this for all values of x, okay, other than the trivial solution, only if A minus lambda I as a determinant is equal to 0. Okay? So if you find the values of lambda that makes the determinant of this matrix, this is a matrix, right? Because I is the same dimension as A, so this is a matrix of the same dimension of A. Okay, lambda is a scalar value, so just a constant value, okay? So A minus lambda I multiplied by x equal to 0. In the general case where the determinant of this is not equal to 0, the only solution for this is x equals 0. There's only one solution, the trivial solution. Tamam? Now in the case that A minus lambda I, the determinant of that, is equal to 0, it means that this equation is valid, can be valid for all values of x, right? So regardless whether x is equal to 0 or not, I can find some lambda that satisfies this equation without requiring x to be equal to 0. When can this happen? If we say that the system is underdetermined, right? Which means that I have less number of equations compared to the number of variables. And this, for this to happen, I have to have the determinant of A minus lambda I equal to 0, right? The singular case, yeah. So solving that, because that is going to produce an equation in lambda. And solving that equation in lambda will provide you with the eigenvalues, right? Which corresponds to those values. So each one of those eigenvalues produces an eigenvector here, okay? So that's kind of how you solve for those mathematically. And the meaning we have been through it. When do you encounter the eigenvalue problem? You encounter them in many problems. One example given in many books actually is the example of multiple objects connected with springs, right? So that system, when you just introduce some initial movement to it and you leave it, you end up with, that's a differential equation example. Maybe I have it here in the slides, I don't know. Yeah. These are just the different, okay. In generally speaking, if we want to talk, we talk about the d x by dt equals x, right? So this general form of ordinary differential equations is known to have a solution which is with some constants on the right side. So this is going to be an exponential. and if you have a set of random variables, you have a set of variables, so instead of x being a single variable, it becomes a set of differential equations. So dx1 by dt, for example, equals a1 x1, and dx2 by dt equals a2 x2, and so on. So the solution, the general solution for that can be represented by x is equal to e to the at, right? Multiplied by some initial condition x naught, and these are vectors, right? And the A is a matrix as well. Okay, so that's kind of the general solution of a set of differential equations that have the exponential solution, right? Okay, so for those ones, for those equations, for example, the eigenvalues of the matrix A and the eigenvectors of the matrix A, specifically the eigenvectors, sorry, the eigenvalues, if they are real versus if they are imaginary, if they are real and positive versus if they are real and negative, they have a very important meaning to the solution of this differential equation. So for example, if the eigenvalues of A are positive real, then this means that this system is kind of unstable because it exponentially grows and it never stabilizes. If they are negative, then it's a damping system. If they include an imaginary component, it means it's an oscillating system. If it's pure imaginary, then it's a cosine or a sine system, so it's a pure oscillatory. If it's complex, the eigenvalues, so they have real part and imaginary part. If the real part, again, is negative and they have an imaginary, so that's damping oscillation. If it is positive real part in addition to an imaginary, that's unstable oscillating system. Okay, so the eigenvalues, they have a very important meaning on those systems, and they can be used for figuring out the properties of the system without even solving the problem. So A is there, right? A, you have it once you have the differential equations, right? So you can figure out the properties of that system without having to go and solve the linear differential equation, sorry, the set of differential equations to figure out the properties of the system, okay? Anyways, that's the big example or the most common example given for those eigenvalue, eigenvector problems. I'm not gonna spend a lot of time here. I'm just gonna go quickly and look at, how to solve for the eigenvalues and eigenvectors. I wanted just to show us. Yes, okay. So how to solve for the numerically for the eigenvalues of a particular system. Of course, the classical approach is you have the A matrix, and then you can use the eigen. There is something called eigen function in MATLAB that can give you directly the eigenvalues and the eigenvectors. So it returns both of them. Okay. Another approach, which is well known also in numeric solutions, it allows you actually to do an iterative approach to figure out either the largest eigenvalue or the smallest eigenvalue of a system. If the system has maybe 5 or 10 or 11 or 100 eigenvalues, it does not allow you to get any values in between. You can only use this approach, which is called the power approach, to either get the largest eigenvalue and the corresponding eigenvector. It comes as a byproduct of the operation, or it allows you to get the smallest eigenvalue and the corresponding eigenvector. In many cases, that's what you want. For example, I know.
You mean if the system has multiple natural frequencies?
Yes. So if it has, it has multiple eigenvalues, it means that it has multiple modes. Those modes could be natural frequencies if you are dealing with vibration, but if you are dealing with other properties or physical properties, it's something else. Yeah. Okay. So again, in many cases, when you are designing as an engineer, you are more interested in like the highest or the lowest. You're not really interested in the in-between because the dominant ones are either the highest one or the lowest one, depending on what property you are looking at. Okay. So that approach is kind of an iterative approach, and the way it works is here it's written as an equation, as a code, but the way it works is you try to solve this problem. A is your matrix that you are trying to get its largest or smallest eigenvalue. The approach in its the way when you apply it normally is going to get you the largest eigenvalue. Then you start by putting the matrix A. You put X as an initial guess of an eigenvector, some initial guess, right? And then you get the result of AX. So A multiplied by X, since A is known, and X is a vector that you guessed, right, as your initial eigenvector. Okay? The result that you will get from that, you assume that this is equal to lambda multiplied by the eigenvector, right? So you assume that what you get from putting an initial guess here, multiplying it by A, is going to be the lambda, the eigenvalue that you're looking for, multiplied by some kind of a vector, okay? To figure out the value of lambda, you reduce this vector to its normalized form. So if that vector includes, let's say 5 values, and the largest is 50, then you divide everything by 50. And the 50 comes as your eigenvalue, right? Now you take that value and you plug it again into the equation A multiplied by X. So instead of your initial guess, okay, you take whatever you got from here and you plug it again here. The normalized one, okay? Once you take that and you plug it here, you will get a new expression on the other side. That new expression that you get on the other side, again, normalize it, and then take whatever you get and plug it again. If you keep on doing this operation, and every time you can actually calculate the amount of error between the current eigenvalue and the previous eigenvalue, the normalized error, right? So the error is calculated based on the eigenvalue, not the eigenvector, okay? And you will see that at some point the error is going to be small, and you will see that the eigenvalue that you are getting is kind of stabilizing, and then eventually also the eigenvector that you get is not going to change that much. And at that point you stop, and whatever you have on the right side, the normalized vector is the eigenvector, and the value that you have there is the largest eigenvalue. Now if you want to get the smallest, you do the same operation, but instead of using A here, you use the inverse of A. So you start this equation, and instead of using the matrix A, you use the inverse of the matrix A, and then you keep repeating the operation. Whatever you will get on the right side when you stop is going to be the smallest eigenvalue of that system, and the vector, the corresponding eigenvector next to it. Okay. What?
I didn't get the last.
Last one, if you, okay, the operation that we did iteratively now with A multiplied by some initial guess X, and then you get something here, normalize, and then you plug it in, and so on until you stabilize. The end of this operation is going to be lambda, which is the largest eigenvalue, and the corresponding vector is going to be the corresponding eigenvector to the largest eigenvalue. Finished? Right. What if I want to use the same operation but to get the smallest eigenvalue and the corresponding vector? All what you need to do is to go to this equation, and instead of using A, you use A minus 1, the inverse of the matrix A. And then you do the same iterative operation. You start with the guess, you plug the guess as X, but multiplied by A minus 1, you will get something on the right side. Take the normalization, then the vector that you get, plug it again, multiplied by A minus 1, you will get something. Do that iteratively, and then once you stabilize, the lambda that you will get in that case is going to be the smallest eigenvalue, and the corresponding vector that you will get is going to be the corresponding eigenvector for that smallest eigenvalue. Tamam? Okay. I mean, you can guess to some extent why this is happening. It is as if you are multiplying the matrix A by itself multiple times, raising it to higher and higher and higher powers, right? Because whatever you get here, right, is going to be a result of A multiplied by something. And then you take that, plug it in, and it's multiplied by A again. And then you take it and plug it in, and it's multiplied by A again, and so on. And when you are doing this, the larger eigenvalue within that system are going to keep amplifying, and the other ones are going to slowly grow as compared to the largest one. And that's why at the end, what you will get out of this is going to be the largest. Now, if you want to look for the smallest, what would you do? When you flip, when you inverse the matrix, you know that the eigenvalues of an inverse of a matrix are 1 over lambdas of the original matrix, right? So now the one that gets amplified better or grows faster than the others is the smallest eigenvalue. Okay? So that's why this operation works both ways only, but it cannot get you anything in the middle. Okay. Again, just a description of the power method that we have been through right now, and it shows you also how to calculate the error at every single step. And this talks about another way of solving for the eigenvalues in MATLAB. Either you can use directly the eigenfunction, right? Just gives you the eigenvalues directly. Or there is another way, I don't know if they have described it here, no. There's another way, which is you generate the polynomial from the matrix itself, and that polynomial function is going to be actually the determinant, and then you get the zeros of the determinant. So you solve the determinant, right? The determinant of the matrix is going to produce kind of an equation in lambda, and then you say solve or give me the zeros of that, which are going to be the eigenvalues, right? So that's another approach to get the eigenvalues. And I'm not going to go into civil engineering, guys, so dynamics of a 3-story building, I'm going to leave that for you to go through. It just shows you, as you mentioned, the modes of operation. So the dynamics of those, mode 3, mode 2, mode 1, each one of them is to different eigenvalue. And the worst case one is the one that has lots of oscillation into it, okay?